Hello grade 11s, in this video we're going to be looking at Lenz's law, and this is basically looking at the direction of the induced current as well as the direction of the magnetic field that is created by the induced current. In previous videos in the electromagnetism playlist we looked at things like Faraday's law, electromagnetic induction and magnetic flux, so check out the playlist for those videos, but let's jump right into this video. As I mentioned in previous videos in this playlist, we looked at the magnitude of the induced EMF. We used Faraday's law to calculate this magnitude. However, Faraday's law did not give us the direction of the induced current. It gave us the magnitude of the induced EMF, which we got using this formula, and then we could work out the magnitude of the induced current, so the amount. But it never told us anything about the direction of the induced EMF. So just to recap, when there's relative motion between a magnet with its magnetic field and a conductor, so when there's motion, so for example, when the magnet moves into and out of the conductor, there will be an induced EMF, in other words, an EMF that is created along the ends of the conductor, which is a voltage, and therefore an induced current. What you also know from previous lessons in this playlist is that if there's a current flowing through a conductor, so a current carrying conductor, a magnetic field is produced around that conductor. So we've got a magnet moving in and out of a conductor, and that creates an induced EMF, which creates an induced current. That current creates its own magnetic field. At this point in time, we only know how to work out the magnitude or the size of the induced EMF and current, but in today's lesson, you're going to learn how to work out the direction of the induced current, so the direction of the current that is created and the direction of the magnetic field that is created because of this induced current. This section is quite complicated. There are things creating things, and those things create other things, but I hope you're following me. So today, we're going to be using Lenz's law to determine the direction of induced current, and you can add there the direction of the magnetic field as well. So plus direction of magnetic field, and that is the magnetic field that surrounds the induced current. Let's jump right in. Now, this is what Lenz's law says. You don't need to know about defining Lenz's law, but you do need to understand it. So Lenz's law says the induced current, so the current that is created, flows in such a direction so that the magnetic field generated by the conductor will always oppose the change in magnetic flux. That is a massive mouthful. That is a lot to understand. But breaking it down, what I did is I tried to break it down in my own words. What it basically says is when we create an EMF, we're going to create a current. That current is called induced current. The direction of that current, okay, we're speaking about the direction of the current, which is determined by Lenz's law. But that current has its own magnetic field. And the direction of that magnetic field is in such a direction that it wants to go against the other magnetic field. There's a lot going on. There's a magnetic field that creates, so a change in flux, which is it's got to do with magnetic field, that creates an EMF, that creates the current. The current has its own magnetic field, and that new magnetic field wants to do the opposite of what the old magnetic field is doing. So basically, the induced current has its own magnetic field that opposes the change that initially produced it. Okay, a lot going on. I know, stay with me. Hopefully, as we do examples, all these words will start to make more sense. So just to recap what we know so far, we have a magnet, as you can see over here. The magnet has its own magnetic field. Okay, so that's like the initial magnetic field. We move that magnet into and out of the coil. When we move that magnet into and out of the coil, there is motion, so relative motion, and there is a change in magnetic flux. This induces an EMF. This creates an EMF. The EMF creates a current, and the current that flows through the coil creates its own magnetic field. Now think of it like this. The new magnetic field that is created and the old magnetic field, they're at competition with each other. They are doing the opposite of each other. So that's why it says over here, the induced current has its own magnetic field that opposes the change that produced it. So it wants to do the opposite of the thing that created it. And what I mean by this hopefully will become clear as the lesson goes on, but just I want you to stick with me, follow me, hopefully you understand. If we push the magnet into the coil, the induced current creates its own magnetic field that wants to push the magnet out. Okay, so we push the magnet in, we're increasing the magnetic flux in that direction, we're pushing the magnet in. The current that we create makes its own magnetic field that's like, I want you to leave. So it wants to do the opposite. So if we push the magnet in, the new magnetic field wants to push the magnet out. However, if we pull the magnet out, the induced current creates its own magnetic field that wants to pull the magnet back in. So it wants to do the opposite. If we push the magnet in, the induced current will create a magnetic field that wants to push it out. If we pull the magnet out, the induced current creates a magnetic field that wants to pull it in. So just keep remembering that it wants to do the opposite. Now, what do we mean by opposite? First, you need to understand that like poles repel. So if you have a north pole and a north pole, so think of one magnet, take the north pole of one magnet, the other magnet, the north pole of that magnet, you have north pole, north pole. They're going to repel. Or south pole, they're going to repel. However, opposites attract. So if you have a north pole and a south pole, they attract each other. Okay, now with all of this in mind, keep following my logic. So if we push a magnet in, so take a look at this picture over here. Here's a magnet right over here. We're pushing it into the coil. We're pushing the magnet in. There will be an induced current. And we can see that over here indicated by the arrows. There's now a current flowing through the coil. The galvanometer is deflecting, which means there's a current. Okay, so we push the magnet in. There's now a current. That current creates its own magnetic field. And that magnetic field is going to want to push the magnet out. So we are pushing the magnet in. The new magnetic field is going to want to push it out. Now, how do we get rid of a south pole that's coming in? What would get rid of a south pole that's coming in? So basically, how do we repel a south pole? We need to create another south pole over here, which means the north pole would be over here. Think about it. This south pole is going in. Remember, the induced current creates a magnetic field that wants to do the opposite. So it wants to push this south pole out. The only way you're going to repel a south pole is with another south pole. So the induced magnetic field will have a south pole on the right-hand side of the solenoid and a north pole on the left side of the solenoid. I hope that makes sense. Let's look at another scenario. If we pull the magnet out, the induced current creates a magnetic field that wants to pull it back in. Remember, it's always doing the opposite. So we're pulling the magnet out. The induced current is creating a magnetic field that's like, no, come back. So take a look at the diagram. Here's the south pole. We're pulling it away. How do you attract that south pole back? How do you get it back to you? You need to create a north pole over here. And therefore, if there's a north pole created over here, the south pole will be here. So take a look at that picture. When we push the magnet in, the north pole gets created on the left, the south pole gets created on the right. When we pull the magnet out, the south pole is on the left and the north pole is on the right. And this is the case when we are pushing or pulling out a magnet with the south pole closest here to the solenoid. Okay, so just remember it wants to do the opposite. So that is basically how we find the direction of the magnetic field, which side the north pole's on, which side the south pole's on. We'll practice a few more now, but remember, Lenz's law also allows us to find the direction of the induced current. Now, how do we do that? If we know which side the north pole is and which side the south pole is, we can use our right-hand rule to figure out the direction of the induced current. So, when your thumb points towards the north, so from the south to the north, towards the north, your fingers will curl in the direction of the current. So look at this person's right hand. They are pointing their thumb to the north and their fingers are curling in the direction of the current. So think of their fingertips as being arrowheads. It's saying that the current is going up and around and down the back. So up around the front and down around the back. I hope that makes sense. So we can figure out the direction of the new magnetic field by looking at the magnet, whether it's going in, whether it's going out, if we want to push, if we want to pull, and then we use our right-hand rule to figure out the direction of the induced current. So here's another example. Here is maybe an explanation that can help you. When in this example, take a look at what's happening. Here's my magnet. Let's highlight it in blue. My magnet is moving towards the loop. Now take note how the North Pole is entering the loop. The magnet's North Pole moves towards the loop. Change in magnetic flux increases to the right. Now remember, we are pushing the magnet in. Okay? We're pushing the magnet in. What does the new magnetic field want to do? It wants to take the magnet out. So how, if we're pushing a north side in, how are you going to push that out again? You need to create a magnetic field that has a north pole over here, because north and north repel. Like poles repel. So if I'm pushing the north in, see, I'm pushing the north side of the magnet in. A north must be created over here, because then that north and this north are going to repel each other. Okay, in other words, the magnet's going to leave again. And if there's a north over here, it means that there'll be a south over here. And that's how we can find out the direction of the new magnetic field. Then we use our right hand to find the direction of the induced currents. Then we use our right hand rule to work out the direction of the induced current. So remember, the right hand rule says that you use your right hand, not your left hand. Your thumb must point towards the north. So look at this right hand, hold up your right hand right now, and you'll see that if you point your thumb towards the north, so your thumb must be pointing left, just like this picture over here. If your thumb points towards the north, look which way your fingers are curling. They're curling up and around that solenoid. That's why my arrows on this picture are going up and around. So the current is going like this. It's going up the front, and then we can't see the back side of the solenoid, but it's going down the back side. Up the front, down the back side. I hope that makes sense. Technically, that is anti-clockwise if you look at this like a circle. So that would be the direction that it's going in. Anti-clockwise as opposed to that way, which is clockwise. Let's take a look at another scenario. So in this scenario, I'm pulling the North Pole away from the loop. So I'm moving the North Pole that way. Remember, the induced current will go in such a direction that the new magnetic field will want to do the opposite. So if I'm pulling the North Pole away, I'm saying, come here, North Pole, we're going away. I'm pulling it like this. The new magnetic field is going to say, no, wait, bring it back. How are we going to, the North Pole's going away. How are we going to attract the North Pole back? We need a South Pole here to attract the North Pole back. So that's why you can see over here, there's a South Pole that's being induced closest to the magnet. And that means that the North Pole will be furthest away from the magnet. Then if we use our right hand rule to find the direction of the induced current, this is Lenz's law, we point our thumb towards the north. So you can see my right hand, my thumb is pointing towards the north, and my fingers curl in the direction of the current. So you can see the current. Remember, think of your fingers as like the little arrowhead of the current. So my current is going up and around. Okay, it's coming down like this, around like this, and then it'll go up the back. Okay, that is clockwise. I hope that makes sense. So just play around, use your hand, see if that makes sense. And just so you know, we always work with conventional current, which is the flow from the positive terminal of the battery to the negative terminal. Now, I don't know if you remember this from our electricity section, but a battery can be represented like this. This is a cell. The long one is the positive terminal. The short one is the negative terminal. So we use conventional current. So we say that current flows from the positive terminal. So from the long side, it flows this way. Current flows that way to the negative terminal. So look at this battery.
the long one is the positive terminal. Current flows from the positive, that's why the arrows are pointing that way, to the negative. Now just take note, see if this makes sense according to the right-hand rule. Use your right hand, see if the direction of current as indicated on the diagram makes sense, and if the poles here make sense, so north and south. So use your right hand, point your thumb towards the north. So let's take a look at current flow. Point your finger, your thumb towards the north, which it is. Look at which way your fingers are curling. So what this is telling me, it's telling me that the current is going like this. The current is flowing around the front. So it's coming down the front like this. So it's saying it's going around. It's going like this. So it's coming down the front and then up along the back. So it's going down the front like that. Down the front, look at your fingernails, the arrowheads. Down the front, that makes sense, to the negative terminal, from the positive terminal, up around the back. So it's going up like this. It's going up along the back. We can't see the back. It's like the dotted lines. Then it's coming down the front. Then it loops around. Up along the back and down the front. Up along the back and down the front. I hope that makes sense. So try this one. I want you to use your knowledge based on this video. I'm pushing the magnet in. I'm pushing the north side of the magnet in to the solenoid. I want you to tell me which side has the induced north pole. So is it going to be a north here and a south here? Or is it going to be a north here and a south here? So first figure that out. And then once you figure that out, tell me which way is the current flowing. Is it going from A to B, or is it going the other way? Is it going from B up here to A? There's a difference. I'm going to pause the video and see if you can figure it out. Once you figured it out, you can do it with me. So first things first, we're pushing the north end of the magnet into the coil. So when we push it in, the new magnetic field that's produced is going to want to get the magnet out. How do we push the magnet out? We need to make a north pole here. Why? Because north and north repel. So we're pushing the magnet in. We want to get rid of the magnet, so we must make or induce a north pole over here, which means a south pole will be over here. Then you take your right hand and you point your thumb of your right hand towards the north like this. Towards the north like this. That means that the current is going from A, it's going up, and it's going, look which way your fingers are pointing, to around the back. Look at which way your fingers are curling. Your fingers, because your thumb is pointing to your north, your fingers should be curling up and around the back of the coil. Imagine you're holding the coil in your hand. So the current is going up, so it's going from A up, then it's going down the back where we can't see it, then it's coming up here, it's going down the back where we can't see it, and it's going up here, and it's going down the back where we can't see it to B. So the current is going from A to B. What about this one? Try this one. So first of all, we are pulling the magnet out. So the south pole is leaving. How do we get the south pole back in? We're pulling the south pole out. The induced magnetic field wants to do the opposite. It wants to pull the south back in. So if we're pulling it out, the induced magnetic field wants to say, no, why are you taking it away? I want it again. So we want to pull the south back. We need a north here because opposites attract. So a north over here, a south over here. Again, use your right hand rule. Point your thumb towards the north. Right, thumb is going towards the north. Look at which way your arrows are going. And also look at which way the wire is coiled around the solenoid. So it's saying up, and your fingers are curling around. So I don't know if you can tell, but what this means is actually that your current is going up the front, down the back. Up the front, down the back where we can't see it. So it's going down, then it's going up the front, down the back to A. So it's going from B to A because it's going up the front and your fingers are curling over like that, down the back. So it doesn't only depend on where the north and the south is, it also depends on how the wire is coiled around the solenoid. That's why this is a very good diagram to contrast that. If you look at the differences in these two diagrams on this picture, The only difference here, you see the battery is, the south is on the left, the north is on the right. The south is on the left, the north is on the right. But in this diagram, the wire goes behind over here. Here, the wire is in front. That makes a difference as well. Just be careful and look. Let's do one more. So this is a past paper question. It says the diagram shows a magnet that approaches a coil with the north pole first. So the north pole is entering. The north pole is going in. The coil is connected to a galvanometer that detects the current. And which side of the coil, left or right, will the north pole of the induced magnetic field be? So they're basically saying we're pushing the north in. Will there be a north here and a south here? Or will there be a south here and a north here? Now you should know by now that if I'm pushing the north in, I'm pushing this in, the induced magnetic field wants to get rid of this. So we must induce a north on this side and a south on this side. Why? Because this north will repel this north. Remember, we're pushing it in, so that means the induced magnetic field wants to get rid of it. Determine the direction of the induced current, say from A to B or B to A. Now again, make sure you can see the way that the coil is connected. A is going over here, then it's going behind. And at B, it's coming out the back there. Okay, so use your right hand rule. Here's my right hand. Point towards the north. Now, when I say towards the north, I hope you figured out by now that I'm pointing towards the induced north, this one. I'm not pointing towards the south, I'm pointing towards the north. And take a look at which way your fingers are curling. We're curling up and around. So it's going up the back, around the front. Up the back, around the front. So actually the current is going up. So imagine the current's going like this, like that. Up the back, around the front. Up the back of the coil, where we can't see it, around the front. So follow it. It's going up and around and around and around and up and around. So it's going from B to A. I really, really hope that this has helped you. I know a lot of learners struggle with Lenz's law and figuring out the direction of the induced current and magnetic field. Please comment down below what else you want to see. Remember to check out other videos in this playlist, past paper practice, things like that. And I hope to see you in a video very soon. Remember to subscribe. Bye, everyone.